How many people are familiar with graphs? Sort of? A little bit? Okay. And I don't think we talked about graphs at all, right? Have not talked about graphs. So I'm going to try to cover this relatively quickly, but the notes are good. So what is a graph? Basically, well, you can ask the same question, what is a tree? A tree is a data structure that has these nodes that are connected by nodes. So you can go from node to node through the different edges. Well, in a sense, a graph is very similar, and in fact, we're going to find out more about what a tree is by understanding what a graph is. So a special kind of graph is actually, a tree is a special kind of graph. So all trees are graphs, but not all graphs are trees. Put it that way. Okay, so if you look at this picture right here, notice that all of these little circles represent what we call nodes, or sometimes we call them vertices. So a vertex can represent basically anything, any little piece of data that we want to put into it. And then we have a connection, and the connection between the two vertices are edges. So a graph is a set of nodes called the vertices, which are all the circles, and the connections are the set of links called edges. So if you look at this example here, notice that V is a set of vertices 1 through 12, and you can see circles 1 through 12 are the vertices that are interesting to us. The edges, for example, is a set of pairs. So if you look at the first edge, what's the value of the first edge? That's the pair. What's the first edge? 1, 2. And that means there's a connection from 1 to 2. Notice there's an edge to 5. So if you go to 2, there's a connection to go to 5. Notice there's no 2, 4. How come no 2, 4? Because 2 does not go directly to 4. No way to go from here directly. So, the set of edges and the set of vertices. Now, the set of, the number of elements in each set is notated by this little vertical lines. The vertical lines is based on what we call cardinality. The cardinality, or the number of elements in a set, is the cardinality of the set. Therefore, the cardinality of V is 12, because we have 12 vertices, and the cardinality of E is 25, because we have 25 edges. Yeah.
Why is not don't have 2 6 directly?
Why is no 2, 6? Because the graph exists in we don't always create the graph. The graph is sometimes a fact of nature. For example, you say, why is there no 2, 6? Well, what if 2, for example, is Knoxville, Tennessee, and 6 is Cincinnati? There's no planes that go from Knoxville to Cincinnati directly on my airline. So it could be just, airline connections. So the vertices could be cities, and the edges could be flights that exist between those cities. Or they could be cities, and this could be roads that exist between them directly. So sometimes there's an edge, sometimes there's no edge. Okay, now a graph is said to be connected if there is a path from any one vertex to any other vertex. Notice that this graph is not connected. Because if I go to 0, I can go to 1 to 2, but from 2, I can only go back to 1. I cannot go, for example, from this area. I cannot go to anything in this area. So this graph is not connected. It's missing an edge. If I wanted to connect it, I could connect, for example, 2 could connect to 3. If I had put an edge between 2 and 3, then I would connect the graph. So my question to you is, how many possible edges exist that would connect the graph? How many edges, possible different edges, could I add into this graph that would connect it? 12. Because I have 3 choices. Any one of these 3 could be connected to any one of these 4. For example, if I connect 1 to 6, I've connected it. Because now I can go everywhere. That's a connected graph. Now, graphs can be used to solve problems in routing. That could be airlines, that could be traffic, buses, cars. They can be used to solve problems in electrical circuits, where adjacent vertices are, for example, they could be, they could be the layout of a chip, in terms of the kind of gates that you have laid out, the AND gate, OR gate, NAND gate, etc. They could be finite state machines. They could represent and solve different problems, whatever can be modeled by a set of places and a set of connections between those places can be solved by, or modeled at least by, a graph. Now notice here we have what appears to be kind of a tree, but it's not a tree. And the reason it's not a tree is because, well, we see in a second why it's not a tree. Anybody know why what looks funny about it being a tree? There's a, yeah, so somehow these two are sharing this node. And somehow we may not know that this is wrong, but we don't feel this is right. And in fact, if you're going to, so, and also, notice another thing here. We also come up with this other new word called a digraph. And a digraph is just an abbreviation for a directed graph. A directed graph is a graph where the edges themselves are directed. Notice in the previous example, I can go from 1 to 2, 2 to 1. There's no arrow, no direction. But here, I can go from A to B, but I cannot go from B to A because the arrow shows that it's a directed edge. So in this case, we have directed edges. So that's what we have, a graph where edges have a direction. Okay? Now, what is a tree? A tree is a digraph. It's a directed graph where one node, which is known as the root, has no incoming edges. There's no edges coming into the root. And all the other nodes are reachable from the root with a unique path. So notice that I can go anywhere to anywhere. If I start at the root, I can get anywhere. If I start at 2, I can definitely get to 11. That's what I have to do. I have to take a left, and a right, and a right. Notice that I can go from 2 to any other node. And the path to get to that node is unique. That means there are no two ways of getting there. And if you think about what we had here, notice that this node is an exception. Because I can go to E with going to the left and the right, and also right and the left. Well, therefore, this digraph is not a tree. Because of the fact that I can reach E from the root 2 different ways. So we shouldn't really call A root, because roots only exist in trees, but they don't exist in non-tree graphs. So therefore, this is not a tree. So therefore, A is not a root. It looks like a root, but it's not. Okay, now sometimes the edges of a graph have a number next to them. That number is referred to as a weight or a cost. So notice that if I go from 4 to 5, the cost is 58, which seems very high, considering that I can go from 4 to 2, and from 2 to 5, a total cost of 9. So now we have a notion of going to some place and paying a lower cost, or a minimum cost. So we can find paths between vertices to be minimum, or perhaps even maximum. Now, graphs can be represented in programming languages 2 different ways, typically. One of them is a matrix, 2-dimensional array, a matrix. Another one is called a list. And the list is called an adjacency list or an adjacency matrix. So if we look at adjacency matrix, let's take a look at that. For a graph G, which is a set V and E that we talked about earlier, the vertices and the edges, the matrix M is an n by n 2D array of values, so that the intersection of row I with column J, or Mij, represents a possible edge, an Ij. If Mij is equal to 1, there is an edge that goes between vertex I and vertex J. If it's a 0, then there's no edge between them. So sometimes there's an edge, sometimes there's not an edge. So if you look over here, you can see there's a graph here, and we corresponded to the adjacency matrix, or what do we call it? Adjacency matrix, yeah. And so, for example, you can see here that's 5 to 3. exists, but notice that 5 to 2 does not exist. Although actually I think it's wrong, because I can see 5 to 2. So I think there's some disconnect here. So it's not a connected example, but it should be. Okay, how about 6 to 2? 6 to 2. 6 to 2, there's no connection. So therefore, 6 to 2, you should have 0. And 2 to 6 is also 0. By the way, if you look at this, is this a directed graph or just a non-directed graph? Non-directed graph. That means if we have an edge ij, if mij is 1, then mji is also going to be 1. If 2 can go to 3, 3 can go to 2. If I can go to j, j can go to I. And in that case, the matrix could actually be partitioned into a diagonal matrix. So we could actually make a diagonal cut here. And if this is truly a non-directed graph, then all I need is just the information bottom of the diagonal. Because if I goes to j, when I is less than j, and j goes to I don't need to even represent it. So I could save some memory representing it. One of the problems with an adjacency matrix is that if you have a lot of nodes, like here, how many nodes do we have in the graph? 7. So therefore, the matrix has how many entries? 7 squared. So if I had 1,000 entries in the graph, then the graph would be what? How many entries? It would be 1,000 squared, which is 1,000,000. If I had 1,000,000 vertices, I would have 1,000,000,000,000 entries. That's interesting. Okay. Because if you think about it, there is an intersection ij for every possible ij. If we're going to have a chip, a computer chip, for example, let's say my hand represents a computer chip. It's a little bit bigger than a computer chip, but let's just say it looks like that. And on that chip, we basically are going to etch a bunch of gates. There's AND gates and OR gates, NAND gates, NOR gates. All kinds of gates are on here. And of course, we're going to have an input in here and maybe an output from the chip. So what happens is the input goes into the chip and then it propagates through the different gates. But you can well imagine that if I have 1,000,000 gates on here, and this gate is right over here, its connectivity is probably most likely only to its neighboring gates. So the signal is going to go from gate to a closed gate. So even though I have 1,000,000 gates, 1,000,000 transistors, let's say, then one transistor is only going to communicate to maybe 2 or 3 other transistors. Which means that if I were to represent this as a graph, I would have 1,000,000 vertices, but only about 3,000,000 edges. Because if every vertex is only connected to about 3 other components, then roughly speaking, 3 times the number of components is the number of edges. But if I were to represent that in software using an adjacency matrix, I would require 1,000,000,000,000 places, but only 3,000 of them would be used as ones. Everything else would be 0. We call this a sparse matrix. A sparse matrix is a matrix where the preponderance or the great majority of the entries are zeros. So just imagine 1,000,000 vertices, 1,000,000 gates, and 3,000,000 connections. So that means we have 3,000,000 connections used out of a possible 1,000,000,000. What's 1,000,000 over 1,000,000,000? Well, what's 10 to the 6 over 10 to the 12? That's going to be 1,000,000. It's going to be 1 over 6. 10 to the 6, right? 10 to the 6 over 10 to the 12 is 1 over 10 to the 6, which is 1,000,000. Times 3 gates per gates, you would have 3 millions. So what's a millionth? Well, how many zeros do we have? So we're going to have a tenth, 100, 1,000, 10,000, 100,000, millions. You're going to have 6 zeros and a 1. So if you have this kind of 1,000,000 gates with only 3 connections on average, you're going to have 6 zeros and a 3. So the density of the ones is going to be 0.000003. It seems to me you're wasting a lot of zeros. So maybe the adjacency matrix is not a very good way to represent sparse graphs. Okay. This is a notation that shows you how you can measure how many vertices, how many edges are coming out of a node, and how many are coming into a node. If you look at vertex 6, and you look across this row, then you will notice that there are 1, 2, 3 ones. And what that represents is the fact that 6 can go to 3, 6 can go to 5, and 6 can go to 7. Therefore, we call the out degree from this node the summation of all the number of non-zero entries, which is 3. So that means the out degree of 6 is equal to 3. And the out degree can be written as Mij, where we fix I at a particular row, make it 6, and then let j go between 1 to n. So fix I at 6, and let j go from here, and that's the out degree. You can see the out degree of node 4. So we're going to fix I at 4, and we're going to count all the j values that are non-zero. And that's 3. The in degree is, if you look over here, for example, we notice that if we look at column 7, the reason this is a 1 is because 3 goes to 7, and this is a 1 because 6 goes to 7. So if you look at all the column entries in column 7, those are all of the incoming edges into that vertex. So if you sum across the column, not across the column, if you sum down the column, then you're going to find out the in degree. And so in that case, what you're going to do is you're going to freeze the j. So you're going to freeze j, which is the column, and you're going to let I vary from 1 to n. So the in degree of node 3 will be the summation in this direction. So it's going to be 1 plus 1 plus 0, 0, 1, 1, 1. Any questions? So we talked about the sparse matrix, and this is just an example that we talked about before, so I'm not going to bother talking about it, but it's the same idea, having too many zeros. So when we have a sparse matrix, it's bad. So we'd like to represent it a little bit more efficiently, and so we use another adjacency structure called adjacency list. The adjacency list looks like this. Now you're going to have all the vertices are in a vector or a sequence, and then what we're going to have is we're going to have a linked list to all of the vertices who are my neighbors that I can get to. So the fact that if you look at 4 here, and 4 goes to 3, goes to 5, goes to 6, it means that the vertex 4 has a direct connection to 3, and a direct connection to 5, and a direct connection to 6. So you can see 4 goes to 3, 5, and 6. 4, right here in this diagram, 4 goes to 3, goes to 5, goes to 6. Does that make sense? So imagine that we had this circuit board with 1,000,000 components. If we had 1,000,000 components, and each of them on average had 3 neighbors, then our list would have 1,000,000 vertices, but their linked list would only have an average of 3 neighbors, which would give us a data structure containing 1,000,000 nodes plus about 3,000,000 nodes, which is about 4,000,000 nodes, which is a lot less than 1,000,000 squared, which is 1 trillion. So that's how to represent adjacency lists for sparse matrices, is just have a vector and just the neighbors you need. Okay, so this is just a different way of representing it. Okay, let's now talk about what it means to traverse a graph. We talked about tree traversals a little bit before, right? We talked about pre-order, post-order, in-order, right? The 3 different traversals. Typical. You can have more. Those are the typical, the hot, top 3, the hot 3, whatever. So traversals for graphs are different. And the reason traversals for graphs are different is because graphs are unusual. Whereas a tree, if you start at the root, you can reach everywhere. In a graph, if you start at a node, you might not be able to get to some nodes. In fact, sometimes you won't be able to get to any nodes. It's possible. For example, if the in degree into a node is 0, what does that mean? Nobody's coming in. So if you're not there already, you're not coming in. Therefore, if, let's say some node H has an in degree of 0, if you don't start at H, you're not getting to H. So that means it depends where you start, where you can visit. So a traversal will give you two pieces of information. Number one, it will give you the set of nodes that can be reached from a given starting vertex. And number two, it will give you the sequence of that visitation. So, if you look at this graph here, which has 7 nodes, notice that our adjacency list identifies where I can go. Notice that from F, I can go to B. So you can see F has an edge that goes to B. This is a digraph. Notice that G can go to D and F. That means G can go to D, and G can go to F. That's it. Pretty straightforward. Now the question is, how do I traverse the graphs? And there are 2 basic graph traversals, which again give you 2 pieces of information. The set of nodes that can be visited, as well as the order of those visits. The first one is called depth first search, or depth first traversal. Depth first means you start at a vertex that you're given, and then you go to the very first neighbor. And then from that neighbor, you go to its very first neighbor. And from that neighbor, you go to its very first neighbor. Can't go anywhere else, because I've been there before. Okay, back up recursively. You went to that first neighbor from here. Is there a second neighbor? Nope, so back up again. Last time you were here, you went to the first neighbor. Is there a second neighbor? Yeah, go to that neighbor. Does he have a first neighbor that you haven't seen before? Yes, go to that neighbor. How many neighbors? 2. I've seen them both before. Well, you can't go there. You can't traverse twice the same vertex, because if you do, you're going to start doing this. You're going to start cycling or looping, and then you won't stop. So we can only visit a node one time. So if I'm at a particular vertex, and I have 2 edges, one goes to D, one goes to X, but I've been to D and X, then I have no place to go, because I've already been there. So what do? Well, since I got here recursively, I'm going to back up to wherever I came from. The last time I was here, I went here. Is there another neighbor I haven't visited? Maybe this one. Okay, so go ahead. That's the basic idea of depth first. Then there's a searching technique or a traversal called breadth first search. And breadth first search basically means that instead of going deep, recursively deeper and deeper and deeper, first neighbor to first neighbor to first neighbor to first neighbor to first neighbor until you can't go anymore, you're going to start and go to your first neighbor. Then you're going to say, do I have another neighbor? Yeah, go to that one. Do I have another neighbor? Yeah, go to that one. You're going to visit all your neighbors first. And you're going to put each of those neighbors into a FIFO queue. What's a FIFO queue? First in, first out queue. So if A can go to BCD, I visit A and I put into the queue BCD. How far are BCD from A? 1 jump, 1 step, 1. So BCD are 1. So next, what I'm going to do, I have BCD in the queue. I'm going to take B out of the queue. I'm going to visit all the direct neighbors of BCD. I only have 1 that I haven't seen before. Let's call that neighbor Q. No, Q is a bad name, because we have a Q, FIFO Q. So let's call it P. So put P. So it's going to be now, so B is out, CD is still in the queue, and then P comes in. So why did I visit that name? So I visit A first, then BCD, then all the direct neighbors of B, then all the direct of C, then all the direct neighbors of D, then all the direct neighbors of P. Who knew it was P? If you knew it was P, then you understand what I'm talking about. If you don't, then I may be talking too fast. We're going to go through this again as an example. Okay. So the idea is we're going to visit all of the reachable nodes in a breadth first search, so that the sequence of visitations will be what we call a monotonically increasing distance. We start at the beginning, distance 0 from the beginning. We visit all nodes that are 1 from the beginning. then we'll visit all the nodes that are 1 from the beginning and visit their closest neighbors. So that means we're going to visit all the nodes that are 2 from the beginning. We're going to visit all such nodes. So that means we will not visit any node that is 4 steps from us until we visited all the nodes that are 3 and 2 and 1 steps from us. So it's called breadth first. We go across. You can do the same thing, by the way, with a tree. So if you look at a tree, this is something you typically don't cover most of the time. How many people have heard of breadth first traversals for trees? Okay, excellent. Where'd you go to school?
RPI.
There you go, RPI. Well, of course they're going to have breadth first traversals. It's a great school. Okay, and when did you graduate from RPI?
2012.
I'm trying to think, because a bunch of my son's friends went to RPI on different years, 2012. So my son actually got into RPI in 2010. He didn't end up going to RPI. But then a bunch of his friends did in 2010, so he would have been a couple of years ahead of him. There would have been like nothing to you. But it was very popular. RPI was very popular. For some reason, a lot of kids went. What town did you grow up in?
Waterbury.
Waterbury. Okay. Well, I live, I'm in Northwestern Connecticut too, so we have some. Not in Waterbury. I used to live in Waterbury at some point, and I actually used to teach in Waterbury. Yeah. Yeah, that's interesting. Where'd you go to school?
For
High school. Not okay. Yeah, go ahead.
It's Holy Cross.
I used to teach at Holy Cross. Did you know that?
What did you teach?
I taught mathematics at Holy Cross. Yes. Over 30 years ago. Yeah. Unfortunately, most of the people I worked with are probably dead or retired. And I'm still great. Well, pretty young when I taught. But no, I still have some connections with Holy Cross. Yeah. Mr. McDonald's still there or not there anymore?
He must not be there, I didn't know.
Don't even know him. My goodness. Wow, 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 wow. There's still a lot of brothers teaching in school? Brothers?
I don't think so. I mean, mostly they're just normal teachers.
So they don't have any brothers?
We had one.
One brother. It's a Catholic school. So you have men of the cloth brothers. Okay, all right. Very interesting. So things have changed. So you graduated in 2008. So you're actually a year older than my oldest son. Graduated in 2009 from Litchfield. Very interesting. All right. I didn't know you were from Holy Cross. That's interesting. And you grew up in Waterbury?
Yeah.
Good, good, good. You playing sports?
We did soccer.
Okay, because everybody's required to be an athlete, right?
Encouraged.
Encouraged, pretty much. All right, very interesting. All right, so if you're going to do a breadth first traversal, what you're going to do is you're going to go from let's keep the kids in sequential order. So therefore, if I start at 2, because I want to, and again, this is a tree. This is actually a binary tree. So what I would do is I would visit 2 first, so I'm starting at 2. Then what would I queue up? 5 and 7 in that order, just to keep it. And the reason I do that is just so if I give you that as a problem on a test, I can check the answers are all going to be the same. I don't have to think of all the permutations of answers that you're going to give me. So, so you're going to go to 2, and then you're going to queue up 5 and 7. When you take 5 out of the queue, you're going to visit 5. So the second node to be visited is going to be 5. But then, what you're going to do is you're going to visit all the children of 5. So you're going to visit?
9.
Well, are you going to visit 9? First, you're going to put 9 into the queue. Then you're going to visit 7. And then you're going to put 2 and 6 into the queue. So now, what are you going to take out of the queue? 9. And you're going to visit 9, and you're going to put 4 in the queue. And then you're going to visit what? 2. And you're going to put nothing into the queue. And then you're going to visit,
6.
and then you're going to put 5 and 11 into the queue. Who's still in the queue?
4.
You're going to take 4 out of the queue. You're going to visit it, add nothing. You're going to add 5 out of the queue, visit it, add nothing. You're going to take 11 out of the queue, which makes the queue empty. You're going to visit it. Okay? And so, the queue will become empty. When you empty the queue, you're done. Now notice that now this is a binary tree, but remember a binary tree is a graph. Every tree is a graph, but not every graph is a tree. So therefore, if this is a graph, digraph, then I could start my sequence of, I could say, hey, start with 7. That could be my starting vertex. In that case, I would visit 7, queue up 2 and 6, visit 2, nothing to add, visit 6, queue up 5 and 11, DQ 5, visit 11, I'm done. That's the basic idea. Okay, so you get the idea. Okay, depth first search. Now, here is the algorithm to do the depth first search. The depth first search is different than what I just did. Depth first means you're going to go as far deep as you can go. So in the depth first search, let's just kind of do it. Let's come back here to the trees. We're familiar with those. There it is right there. So if I'm going to go depth first, let's say I'm going to, now notice that this tree is a binary tree, but it is not a binary search tree, right? I can tell it's not a BST because I have bigger, smaller, and I have smaller, bigger. Okay. But even though it's a binary tree, it's not a BST, I can still do traversals. They might not be as satisfying as if the tree was a BST, because then traversals in order would actually give me an increasing sequence order, whereas not is not going to give me that. So if I'm going to go recursively, so at this point I'm going to go visit 2, and then I'm going to visit my smallest child. So I'm going to go 5. I'm going to visit it. 2, 5. Then I'm going to go to my next child from 5, which is 9. I'm going to visit it. I'm going to visit 9. I'm going to visit 4. I have nothing more to do. There's no other children, so I'm going to back up. Any more children? No. Any more children? No. Any more children? Yes! So my sequence so far is 2, 5, 9, 4. Now I'm going to go down here. I'm going to visit the 7 immediately. Since I'm going in key order, I'm going to visit what? 2 immediately, but there's nothing more going, it can't go any deeper. So I come back on it. Any other children? Yes. So I'm going to visit 6, and then recurse with a smaller child 5. Nothing more to do. Come back up, visit 11, and recurse, them out. So that's depth first. And of course we can do the same with these types of graphs. So what I have here is an example of the depth first search going from the starting vertex of is it 8? 8. I don't know why I don't say it here, but it's 8. Do I say it?
What's your argument for DFS?
I don't see it. Oh, okay, okay. Yes, okay. So we're going to start with A. Now, so let's take a look. So we're going to go depth first. So let's go backwards. We're going to start with A. Is it the same graph? I think it is the same graph. So let's see what's going to happen here. So from A, I must go to B. From B, I must go to, by the way, as we do these traversals, because there are cycles, we always have to keep track of where we've been. So we always have